Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 43. The name of the lecture is noise performance and flicker noise. So, we will be primarily in this lecture look into the noise analysis, what are the various components of noise in a signal and how they behave when you pull down the temperature to cryogenic temperatures. Now, typically, so let me outline what we will be doing and then we will go one by one. So, we will look primarily into the type of noises which are prevalent at cryogenic temperatures. We will be also understanding the flicker noise, the origin analysis of the flicker noise, and how does tuning of the threshold voltage actually helps you to change the flicker noise in a respect. So, these are the few outline of the talk which we would be primarily trying to do. Now, so the flicker is basically referred, so when we say flicker in this case, flicker is basically 1 by f noise, right, and it is inversely proportional to the frequency, right, and that's what you get it. Now, typically the study which many people have done is that they have varied the temperature from 300 Kelvin down to 10 Kelvin, and some of the papers have even gone to millikelvin range and studied the 1 by f noise analysis, right. So, this is the general trend where people have actually used various mechanisms to evaluate the value of the 1 by f noise. Now, the dominant source for this source of noise is basically the carrier number fluctuations. So, if when the carrier fluctuates and the number fluctuates over a period of time, this results in this noise, and the normalized noise is to a larger extent independent of the temperature. The other noise sources are independent of the temperature at several other noise voltages. So, when you actually try to find a normalized noise value, it seems to be independent of temperature, but flicker noise seems to be depending on the temperature to a larger extent. This also depends upon the availability and the position of the traps, which I had earlier discussed to you in other lectures, and its relative position with respect to the carrier parts. Now, typically at cryogenic, if you look at the cryogenic temperatures, right, the CMOS performance is improved in many aspects, which I have already performance actually improves to a larger extent, and this improvement is primarily because of device level enhancement in certain characteristics. One is, of course, as I discussed with you, elevated mobilities, right, elevated carrier mobilities which you get, and then lower threshold and therefore better turning on, and also decreased power consumption. However, what comes into picture and which has not been dealt to a larger extent is the availability of 1 by f noise at such a low temperature, and that tries to demerit the gains which we have been try. However, low temperature, if you look, these are what you see is basically the sort of an advantage, right. So, let us look at the challenges as well. The challenges which you will face, or the drawbacks which you will face, will be basically, if you remember, is dopant freeze out, right. Dopant freeze out is one of them, which we had already discussed in our previous slides. We have also looked into your series resistance will increase, and there is also anomaly in the transient response. So, transient response also shows certain anomalies. We will not go into detail, but this and this are well known by the scientific community. So, within which, because we are dealing with noise, we also need to know that at quantum and at cryogenics at such a low temperature where you are dealing, you need to bring into what is known as a quantum effects, right. So, the quantum effects will try to basically categorize the energy levels, discrete energy levels, and they end up having a large change in the value this thing. Now, there are large sort of research papers and work done by researchers where they have tried to find out the variation of 1 by f noise with respect to absolute temperature down up to millikelvin, right. However, the problem is that the signal floor, right, and the noise floor are very close to each other at room temperature, at millikelvin is very close, right. So, it is very difficult for you to distinguish between a noise and a signal, and therefore, the filter technique applied is rather tedious, right. There have been many research papers which have even taken SOI sort of mechanism, so silicon on insulator. With this basic background now available, because we are entering into a new regime of operation, let us look into the various types of noises which are available at the cryogenic temperature. So this is to a larger extent device agnostic. So, you give me any device and we will be able to find out all these noises to a larger extent. One is the Johnson noise. This is independent of temperature. I am generalizing the noise source, and the first one is basically your thermal noise, right. This is also referred to as a Johnson-Nyquist noise, and it is directly proportional to temperature. So, therefore, very straightforward, as you reduce the temperature, your thermal noise goes down to a larger extent. Similarly, if you look at short noise is still present, but it also depends upon the current and the biasing. Please understand the currents will be very low, your short noise capabilities are very small. However, what is more dominant is basically the flickered noise, right, and this is because the flicker noise per se does not decrease with temperature, but since with respect to the thermal noise initially, so flicker noise was low, thermal noise was very high at 300 Kelvin, but when you reduce the temperature and you bring down to millikelvin region, the thermal noise almost vanishes, and therefore, the flicker noise sort of becomes more dominant in a sense, right, and therefore, it is one of the most important noise which you need to study at cryogenic temperatures. Then you look into random telegraphic signal noise, which is RTS noise, and typically these are very prominent at nanoscale devices, but let us not touch this because we will not be going into too much of nanoscale devices at this stage. You then have a generation recombination noise. So, every time let us say you are working with 300 Kelvin temperature, you will be generating electron hole pairs, right, and they will be also recombining after a finite sort of relaxation time, which means that this formation of electron hole pairs and recombination and thereby giving out energy is basically the reason why you get a generation recombination noise, right. However, we will be focusing at flicker noise because very low frequency, it implies that the flicker noise will be available and they will be more competent or more eligible at cryogenic temperature. Now, if you go through many research papers, one of the research paper has been is quoted here, right. I will give you a quote also. This is basically a TED paper, Transactions on Electron Devices, from where I have taken this discussion. It is basically transaction electron devices which was published in, I will give you the data here, in April of 2025, right, and the page number is 1926 onwards, right. So, those who are interested to look into it can have a look at this paper, and this is basically the first author is basically Pathak et al, right. You can have a look from this paper, which gives you a good idea about the initial. In fact, it gives you a measurement technique also for the flicker noise. Okay, what the authors did in this paper was they took up a low threshold voltage FinFET, again device agnostic in nature, and they were fabricated on a global foundry technology, and they used a hafnium dioxide based gate stack. So, they used a GF, right, GF technology, and this was basically a 12 nanometer FinFET, and this was fabricated on a HFO2 stack gate oxide, right. This was the stack which was available, and then they applied then the width of the FinFET was taken into account and find out the current, but we are more interested in sort of a 1 by f noise or characterization of NFET and PFET. So, typically the methodology they adopted was, let me just show you the methodology so that you can actually see it. It is given in the paper also if you want to have a look. So, I have this drain and I have source and bulk, right. So, this is my gate here, right, and this is my source. Of course, this is body, let us assume, and this is drain and this is gate. So let us start one by one. At the gate side, we give a, what the experimental was done was using a module known as E4727A, and this is basically an input module where you can input a signal into the system. On the drain side, you have one module here, which is given as E4727A again, but this one is basically an output module, right, and body is again controlled by a substrate module, right, and this is again the same E4727A, and this is the substrate module which you get, and this is fed as a body inside, and the source is being fed. So there are two aspects of it, we have a drone and a source. So I have this, so the drain is connected here, right, and the drain is connected to the drain side and the source is connected to the source side, right, for the output, right, and all of these goes to a B1500 parametric analyzer, right. This is a parametric analyzer. We will not go into details of this, but this is a general structure which you get. Again, of course, they are talking to this is trying to manipulate this and so on and so forth. So this is a general scheme of things. These are all independent input sources here, output source here, substrate here, and there is a parametric analyzer which tries to build up CV, IV and so on and so forth for flicker noise. So this was basically done by the authors on a lakeshore cryogenic system probe station, and they were able to finalize the values of 1 by F noise at 8 Kelvin. So this temperature can go up to approximately 8 Kelvin to 10 Kelvin range measurement can be done in this case. Okay. Now, as I discussed with you, therefore, coming back to the original discussion, that if you have a generation recombination, noise is not there. So that is the reason we are concentrating more on the 1 by F noise in this sense. So what is a flicker noise basically, right? So flicker noise is a low frequency noise which is characterized by 1 by F dependency of the in its power spectral density, right. 1 by F noise is also referred to as an excess noise, but for all practical purposes we will say that 1 by F noise is frequency dependent, higher the frequency lower is the noise, and it has got its dependency on the PSD or the power spectral density of the device. Why is it important? Because two things, primarily it indicates the device quality and interface integrity. So if the interface integrity is bad, which means that the interface is not good, you have large amount of traps and there are large amount of detrapping happening, of course there will be a good amount of trapping, detrapping taking place, and thereby indicating that the interface quality is relatively low. Similarly, happens to be an important parameter when we are discussing quantum computing, right, and the reason is in quantum computing you are actually working with very low temperatures, right, where your carrier freeze out has taken place, your on currents are very low, which means that your signals are relatively very low, and if your noise and signals are very close to each other, it is very critical to separate signal in a proper manner without degrading the signal quality, right, and that is where all the problems comes in a larger extent when you deal with the flicker noise. So what is the main sort of origin of flicker noise, right, and primarily they come due to trapping and detrapping of carriers in traps near the interface or the oxide, and therefore if you look very closely as the frequency goes on increasing, since the trapping and detrapping process will reduce, your carrier number fluctuations will also reduce and you will get a stabler flicker noise, or flicker noise will not go on increasing as you move to higher frequency. Second is there are large number of tunneling process and trap distribution which also influence the carrier number fluctuation. So the main reason is basically suddenly the carrier becoming high or suddenly the carrier becoming low, they introduce a noise, and this high or low will also depend upon how the carriers are getting trapped or detrapped from the interface and oxide trap charges, primarily near the interface trap charges, and they are sitting somewhere about maybe few angstrom inside the oxide layer, maybe 1 or 2 angstrom inside the oxide layer, and they release when there is a frequency, input frequency is small, they get released and they get accepted by the trap, because these are low energy sort of traps available to us. Second is that there is also a second case that phonon scattering is there, and that affects the carrier mobility. When the carrier mobility gets affected, there is introduction of the noise which happens. And therefore, a large study has been done on carrier number fluctuation across the temperature range. There are large number of theoretical advances being made in the modeling scheme as far as flicker noise is concerned, and these fluctuations happen over a period of time, and these fluctuations are normalized with respect to time to get the overall sort of a flicker noise in that period of temperature range, right. Okay. So, let us look at what are the key analyzing features of the flicker noise at cryogenic temperature. Now, you will have, so the main observation, if you look very carefully, is that there is at very low temperature, the temperature independent normalized noise is there in advanced FinFETs as well as in bulk MOSFETs. So, both in bulk MOSFETs and in FinFETs you will have temperature independent normalized noise being available, right. Similarly, there is a uniform trap distribution at low temperature. If what is the trap distribution is how the traps are distributed with respect to energy and space within the FinFET in this case, or bulk oxide in general, right. And therefore, as a designer you need to study, when you are actually studying the flicker noise, is that when you lower down the temperature, does the distribution change drastically or not, right, and that is a key observation which designer working with noise needs to keep in mind. Now, now let us look at the behavior. As I told you, carrier fluctuation is the primary source, but also the depth of the trap, right, also is responsible for various noise profiles. Now, noise as such is a statistical phenomena, it is fully random, and therefore, you cannot predict a priori the value of noise beyond a particular point. However, you can find the average value of the noise over a period of time, right, and that can be done also with respect to period in temperature. Now, the problem or the challenges which are there in characterization of the flicker noise is, of course, the equipment required or the measurement technique should be very good, because at such a low temperature you require very specialized setup wherein external noise sources do not influence the internal noise of a cryogenic system. Similarly, both number and mobility fluctuation will contribute, and therefore, since the mobility also changes as well as the number changes, the analysis is quite complicated, right. The last part is that I discussed with you trap distribution, and second is the proper fabrication technique. Very precise fabrication technique needs to be highlighted in order to generate a very low flicker noise, right. That is the sort of a bottom line in terms of challenges which you face in most of the cases. Now, if you plot drain current versus, if you plot IDS, drain to source current versus temperature, of course, here, and this is 300 Kelvin, let us suppose. Then if you take an N channel device or a P channel device or whatever you want to do, it is something like this. The general trend is something like this, right. So, there is an increase in temperature for a low value of gate voltage, right. Similarly, if you plot the transconductance also, you will get the same value. If you plot subthreshold slope, which we have already done in our previous cases, you will see that the subthreshold slope actually starts to reduce at very low values of temperature. So, this is a general trend of SS, this is the general trend of ID versus temperature. This is also with temperature. So, as the temperature drops down, your subthreshold slope will be even smaller than 60 millivolts per decade. So, if you put 60 millivolts, this is what you get at 300 Kelvin, at 3 is higher than 60, and then it actually goes below 60 at this thing, which means that the switching thresholds are much higher. Now, one important point which you should note is that all these devices, when you do a practical application using characterization of flicker noise, we also consider the variability issue of the devices, which means that how the devices from batch to batch or lot to lot, how is the devices varying, and typically a range or a percentage of approximately 5 to 10% is a sort of a justified and a respectable sort of we can take. Now, how do you do a characterization in case of a cryogenics, right? So, we need to do a PSD or the power spectral density measurements for specific frequency, for example 100 hertz, right. And we want to look how does the drain current depend, or how does the noise depend on the gate overdrive voltage. Gate overdrive is the gate minus the threshold voltage as well as the drain current, right. So, overdrive voltage and drain current, how they affect the noise phenomena, especially 1 by f noise, right. So, that is one important point which you should keep in mind. Now, let us look at some important formulas. Noise power density relationship is given as SID, which is the noise here, and about ID square, which is proportional to V overdrive to the power minus m, where m can be 1, 2 or 1.5. Various fluctuation mechanisms are predicted by this small m value, and from here you can actually predict the trap density in a normalized noise using normalized noise technique. So, let us go one by one and see where we are. So, on the x axis is a power spectral density which we so this is SID is the power spectral density, and if we divide by IDS square we get the normalized flicker noise, and therefore, on the y axis you have a log scale flicker noise being available, and on the x axis you have the overdrive voltage which varies from 10 to the power minus 1 volt, which is 0.1 to approximately 1 volt. So, 1 log scale on the x axis and at least 4 log scale on the y axis, and the blue ones are basically your 10 Kelvin graph. This is the 10 Kelvin, and this one is effectively 300 Kelvin measured value, and this is for N FinFET and this is P FinFET. One thing is very clear, your VDS is 0.5 volts has been maintained and the frequency is 100 hertz which you maintain. One thing is clear, that there is not a much larger difference in the value of your flicker noise, at least in PFETs, right. The PFET, if you look very closely, are all bunched together. So, these are all bunched together here, right, and the noise which you calculate is an inverse proportional to the square of the overdrive voltage. So, higher the overdrive voltage, lower is the flicker noise which you see, and that is true also, right, because you are pulling the charge carriers closer to the interface and your flicker noise goes on decreasing. What we have kept is 100 hertz, and we have kept the frequencies is basically low frequency, and therefore, a 1 by f noise is relatively larger, and we try to calculate at VDS equals to 0.05 volts, and we have used two potentials here, though not shown here explicitly, but when we use close symbols it is basically your regular VT, and SLVT is basically super low VT, which are open symbols. So, the open symbols, this one is your super low devices which are, and the closed one, which is this one, let us suppose for example, is a regular threshold voltage. So, two flavors of threshold voltages have been used here, and of course, the blue circles are 110 Kelvin and the red circles are 300 Kelvin. Now, let us look at the impact of threshold voltage on the flickered noise, right. And so, they have plotted it at 10 Kelvin. When you do, the regular threshold voltage slightly exhibit a higher flicker noise as compared to low voltage flicker noise, which means that the type of threshold voltage device which you are taking affects the flicker noise quantitatively. However, interestingly, at 300 Kelvin there is no much difference between the RVT and SLVT FinFETs, because at very high temperature thermal noise takes over, right, and these noise gets hidden behind the thermal noise, and therefore, they are not visible actually in a sense. In most of the cases, flicker noise, and this is very important, follows a trend of V 1 by V over. So, this is basically overdrive. So, it is basically inversely proportional to the square of the overdrive. So, which means that higher the overdrive which you get, lower is the flicker noise which you will get. Now, which effectively means that better the gate control over the channel, you have lower the flicker noise in that case. Now, in PFET, as I discussed with you earlier also, independent of the temperature, the value of the flicker noise is almost the same for both 10 Kelvin and 300 Kelvin. Again, the dependency is consistent for both PMOS and NMOS. If you see, it is a linear fall taking place in both the diagrams, and this suggests that the carrier number fluctuation is dominant in both the cases, right. The increase or decrease in the number of carriers impact the nature of the flicker noise source. Now, let us look at the threshold voltage tuning. has an impact on the cryogenic and in N channel FinFETs. Now, at room temperature, the threshold voltage tuning does not effectively change the flicker noise, and the reason is very simple. Flicker noise is ordered smaller as compared to thermal noise in those cases. And as I discussed with you even in the previous slide, that both N FinFET and P FinFET, for that matter N FET and P FET bulk also, will show inverse square dependency on the overdrive voltage, right. And therefore, the primary reason can be found out therefore by the enhancement of the charge carriers, right, or the generation of the charge carriers at such a low temperature. So, that is the basic impact of voltage tuning on the flicker noise. With this, let me recapitulate what we learned in the present half an hour. Is first thing is we understood what is a noise, right. We also understood various types of noise and its dependencies. Then formulation of noise, measurement technique, basic measurement technique for both N and P. Fifth, we saw that P was more tightly bound in terms of variation, whereas N was slightly deviating from its path, both at 10 Kelvin and also at 300 Kelvin. Why is it important? This gives me a brief idea about this study will give you a brief idea about 1 by F noise contribution to the total current when you are actually working at cryogenic temperatures. I hope you enjoyed the lecture. Till we meet next time, goodbye.